Good day, welcome to Molecules Part 2, Lewis structures. Okay, so we're going to start talking about structural formulas, or in this case, one particular type, the Lewis structure. But to think about those, let's talk about the other formulas we talked about. The empirical formula was the ratio of atoms. The molecular formula was the total number of each atom. Structural formulas not only show the ratio and the total number, but also show the arrangement, the order in which the atoms are connected. Which atom is connected to which other atom? Because remember, unlike ionic compounds, covalent compounds are discretely connected. Electrons are being shared between two specific atoms. Well, who is sharing with whom is what we're going to be looking at. The core one that we're going to look at is the Lewis structure, which shows the valence electrons and which ones are being shared with whom. Now, in 152, we're going to kick this up a notch and look at other structural formulas that work better for big fluffy things. But right now, we're just going to go with the basics and go for Lewis. G and Lewis pioneered the use of chemical symbols, and, well, you do something cool, it gets named after you. And with these guys, we're going to be doing this governing rule called the Octet Rule. Now, for some atoms, it's the octet suggestion, but for survey chem, we're going to kind of ignore those atoms. Just be aware that especially sulfur and phosphorus totally violate the octet rule on a regular basis. But we're going to mostly stick to atoms in the first two periods of the periodic table, which generally stick right onto octet rule, with a couple of exceptions. Now, when we're writing a Lewis structure, we're going to look at that octet rule. And the octet rule's goal is that every atom wants 8 electrons in its valence shell. A hydrogen is going to want 2 because it's hydrogen. And a couple of them, well, there's some exceptions. We're going to try and avoid the exceptions other than hydrogen. Okay, I'm not going to read this. Let's go through this step by step. Now, first off, there are 2 ways of doing this. I'm showing you the way that generally works better for organic molecules, things that we're going to encounter in 1152. For crazy inorganic things that have metal ions or other bizarre phosphorus usually containing compounds, there is the more official way of doing Lewis structures, and I'll let you read your textbook for that one, because honestly, it's harder if you're dealing with carbon, and usually you're dealing with carbon. So let's deal with this guy, and first off, we need the Lewis symbol to do it in this approach. And you've already seen this. So we're going to take our element, and we're going to figure out how many valence electrons it has. Once again, I go over the periodic table, and I count which group it is in, skipping the transition metals. Now, I draw an invisible box around my element, and I start putting the electrons on it. 1 on each side of the element. Now I have 4 electrons on 4 sides. Do I still have electrons left over? For oxygen, I sure do. Not always will I have it. If I have something like hydrogen, there's only 1 electron to start with. But oxygen's got some left over. So now they start getting roommates. You start pairing them up. So now you put 1 on to form a pair there, and you put another pair there. When you have electrons paired, these are known as lone pairs. They're chemically different from their unpaired counterparts. And in general, lone pairs don't do a lot. They'll occasionally interact with metals or stray hydrogen cations, but for the most part, they don't do a lot, which is kind of good. Now, once you're done, of course, ditch the box if you actually drew it out, and thus you have your Lewis symbol. Okay, let's draw a structure. When you're drawing your structure, first thing you need to do is take your molecular formula and write the Lewis symbol for each one of the atoms in it. Now, when you're just starting, I recommend if you've got 3 chlorines, write 3 chlorines. Once you get experience, then you can just write 1 chlorine and know, hey, I need to put it on 3 times, and eventually you already have chlorine memorized. You don't have to keep writing it by itself. But you write the Lewis structure for each one of these guys. Now, what you want to do is start making pairs. Your lone pairs are already paired up, but those unpaired electrons are not. if an unpaired electron is left all by itself, it's called a radical. They're incredibly reactive because they want to be in a pair. This is kind of the bad dating advice model of chemistry. You know, you got the single folks who just are trying to get a date. Well, the electrons are the same way. Okay, so you're going to start making pairs. So you want to pair every unpaired electron with another unpaired electron. A couple of tricks to this. For starters, the least electronegative element, the one, once again, starting your chemical formula probably, and definitely the one that is to the bottom left on the periodic table of the other ones, is probably going to be in the middle. Obviously, if it only has one unpaired electron, then it's probably not going to be in the middle because, by definition, it's the end. Okay, so you guess who's probably going to be in the middle? You start connecting them. Two major things to keep in mind when you're arranging these guys to start forming pairs. Most atoms do not like to bond to an atom of the same type. Carbon is the major exception. That gives us the entire field of organic chemistry, its ability to bond to other carbons. But for the most part, other elements don't like to do it. They will, but not that often. Second thing, while not unheard of, rings are rare and generally are going to contain carbon and usually 5 or 6 atoms in size. So when you're assembling these things, assume, unless you got a good feeling otherwise, that unless carbon's involved, 2 atoms of the same element are not going to be directly connected. And even if carbon's involved, you probably don't have a ring shape. So that you would, if you connected the dots, you would get a ring by having 3 or more atoms paired up. Now, if you're drawing a few of these guys and getting a little bit fancy, things can get a little bit more interesting. So you can have a covalent bond between 2 atoms. We call that a single bond, and we've been talking about them incessantly. But it turns out that atoms can share with their partner 2 electrons, 4 electrons, and even 6 electrons, not more than 6. Since each pair of electrons being shared is considered a covalent bond, we call those a single, a double, and a triple bond, respectively. So a double bond is sharing 4 electrons. Well, you need to draw this. So what you want to do is, if you have a scenario where you think you have a double or a triple bond, you get to angle your Lewis structures or completely kind of fudge that square shape and pair up to 6 electrons between 2 atoms. You can do that. You cannot pair 8, only up to 6. And once again, they're going for pairs. So you're looking at 3 pairs, not just 6 random electrons. If you have a polyatomic ion, so you have a molecule with a charge, then you simply deal with the charge the same way you would as an atom. So if it's a cation, for however many positive charges you have, you subtract that many electrons. If it's an anion, well, you get to put more dots on for however many electrons extra you have for that charge. Generally speaking, this is stuff we usually like to throw at you in the 12 series, not so much in the 11 series. So you might see one of these. Don't expect a ton of them. Okay, once you're done, you've made your pairs. Most of the time, people like to clean them up. So converting every pair into a line. So you'll notice that this chlorine and that phosphorus are sharing those 2 electrons. Well, that's those 2 electrons. They're in a line now, but it's much cleaner this way. We see the relationship, and it's not just sea of dots, which makes life easier. Well, that's it for Lewis structures. They're pretty straightforward, but they do take some practice. So time to practice them. Last part, we're going to be talking about forces that hold molecules to other molecules. So kind of those long distance stuff, what we call intermolecular forces. So see you in part 3.